At queuing. And for queuing, just follow me carefully. These are the formulas we're going to be using. That's one thing. Now, there are some things you need to know about queuing. So the queuing theory is stating that we can find the characteristics of a queue. Everybody knows what a queue is, right? A queue is a line, basically. You guys should know that. Queue and line is the same thing. We can find the characteristics of a queue. You can find how many people are in the queue. You can find how many people are not just in the queue, but the person gets served. So that's the entire system, and I'll show you that. So we can find all of that. We can find the probability that somebody has to wait if they come into that system to get served. You can find number of persons or number of units in a queue. You can find number of units in a system. You can find the time spent in the queue and the time spent in the system. So here we have two things that are important: your arrival rate, which is called lambda, and your mu, which is your service rate. Mu, mu, right? Lambda and mu. Now, for this model to work, right, lambda over mu must be less than 1. Okay? And by less than 1, we're taking, I'm just throwing this out. It's going to be between 0.2 to 0.99. Right? It's going to be somewhere in between there. Okay? If you found your lambda and your mu, or your lambda over mu, and it's not within this range, then something is wrong. You need to look back at your lambda, look back at your mu. The other thing is that you see we're talking about arrival rate and service rate. So it's the number of units you can service in a particular time. Now that time has to be consistent for the two, because you see you're doing a ratio, lambda over mu. So you can't put hours over seconds, or you can't put minutes over seconds. So you have to bring all of them to the same time span, right? So if it's seconds, it's seconds. If it's minutes, both of them have to be in minutes, right? Number of units per minute. All right, is that clear? Yes? So far, okay?
Yes, sir.
All right. So now, and let me explain what the queue is and what the system is. So let's say you have 3 persons in a queue. There's 1 cashier. I'll use cashier because you guys are familiar with that, joining a line to get some cash. This system only uses 1 cashier all the time. So your cashier is over here, right? So here we have the queue. How many people are in the queue here? Can you see? Tell me.
3.
3 people are in the queue and 1 person at the cashier, right? Are being served. Cashier is serving 1 person, right? Are you seeing that? Yes or no?
Yes, sir.
Yes, sir.
Exactly. So this is what we call the queue, but the entire thing is called the system. That's easy enough. Queue, persons in the line, system is persons in the line plus persons being served. That's easy enough, right? Yes, I just push cashier to make you understand, but it's being served, basically, right? All right. So that's how you differentiate the queue from the system. Okay, is that clear so far? Also,
Yes, sir.
people are going to come back to me once you start working the problems on how you get this and how you get that. So let's just establish this from now. All right. So the formulas are the probability that there's no unit in the system. So the entire system is empty, is P naught. And the formula for that is 1 minus lambda over mu, right? Yeah, simple enough. PW has 2 meanings. It means 1, probability that an arriving unit has to wait for service. And 2, utilization. More or less, utilization is what we're going to be using it for a lot. PW is lambda over mu, all right? And we're always going to find out lambda over mu first things first. Your P subscript n is equal to lambda over mu to the nth power times P naught. So you can calculate P naught from up here. And if you want to know probability of 5 units in the system, so n now becomes 5. So it's lambda over mu to the 5th power times P naught. Okay? That's the probability of 5 units in the system, so to speak. Then we look at the number of units.
Excuse me, sir.
Yes, go ahead.
Just to confirm what you were saying a while ago about the to the fifth power, you just replaced
N
the
is
5 with
N
N.
can be any number.
Okay.
3 units, 5 units, 10 units, 20 units, N. Okay, I just used 5 as an example.
Okay.
L is the number of units. LQ is the number of units in the queue or in the line, right? L is the number of units in the entire system, okay? WQ is the time spent in the queue. So we're talking about time now, not just the number of persons in the queue, but the time spent in the queue is WQ. And the time spent in the entire system is W. So a quick way to remember this, and I usually just tell students this, if you're talking about probably there's all up there. But when you get to finding out what you want for the queue or number of units will always be an L. So there's only 2 things to remember, the L's and the W. LQ is the number of units in the queue as the subscript Q, right? And then L is just the other thing, is a system, because only Q and system that we're talking about, right? And W is going to be the time, WQ is the time spent in the queue, and W is the time spent in the entire system. Now, the easiest way to remember what W is and what L is there's only 2 things you're looking at, right? W, I like to put a watch. W for watch, and watch tells time. So WQ is time spent in the queue, and W is time spent in the system. There's only system and queue. Is that clear? It'll come while we're working some more problems anyhow. All right, so now that's about everything you need to know about the theory of the queuing system that we're going to be using, the model that we're going to be using. The arrival rate basically is constant in nature, and the service rate is usually exponential in nature. But we'll come to all of that when we start working the problems. All right, but any problem you get will conform to our model that we're using, where it's only one service, one person servicing, or one unit can be serviced at a time, and then that's the queue. All right, so let's get straight into working the problems. Let's ensure you have your queuing tutorial out, please, so you see where the numbers are coming from. Please have your tutorial out, queuing, so that people don't ask where numbers are coming from. And please have a calculator at hand. As I've said this in every class, and this is almost the end of the course now, you must know that you need a calculator to do this. All right. All right, so the Reggae Rhythm Electronics Corporation retains a service crew to repair machines breakdowns that occur at an average of 3 per day. It says approximately a pass on in nature, right? The single man repair crew can service an average of 8 machines per day with a repair time distribution that resembles an exponential distribution. It says, what is the utilization rate? What is the average downtime for a machine that is broken? How many machines are waiting? And what's the probability that no more than 1 machine is broken and waiting to be repaired? Does everybody have a calculator at hand? Does anybody
Yes, sir.
have a calculator at hand? Because you're gonna be doing some numbers for me. If I'm giving you the theory, then you must can plug in 2 numbers in a calculator and get an answer, right? All right, so everybody see the problem that we're looking at? Let's
Yes,
look
sir.
at the procedure to working this out. First things first, you're going to find your lambda and you're going to find your mu. That's the first thing to do. So for lambda, which is our arrival rate, is 3 per day. Yeah. Everybody see that? And your mu, which is your service rate, that one serviceman can service 8 units per day. Yeah. So first thing I want to do is make sure it fits the model that we're going to be using. So I say lambda over mu is going to be equal to 3 over 8. And what's that equal to? 15 people with calculators. Come on, somebody must understand what is 3 over 8.
Point 375.
0.3.
75.
We call it 0.38.
Yes, sir.
Right, everybody get this? For lambda over mu, so it conforms.
Yes, sir.
Right? Conforms. Now that it conforms, we now start to attack the problem. A. Now, to find anything that we're looking for, you need to say you're looking for utilization. And utilization is PW, right? So PW is what I'm looking for utilization, right? I put a question sign there, and I said PW equal to lambda over mu. I've found my lambda over mu before, which is a good thing, and that's why you should always do this first. So my utilization rate is going to be equal to 0.38 or 38%. By utilization, you're just saying, you're looking at how efficient you are, how the process is, and how much capacity you've used up. So you're only using up about almost 40%. So this is inefficient. You can probably tell this one serviceman that he can come in for half the day, basically, if you don't want to pay him for the whole day. And you'll still be fine. You'll be cleaning up all the machines that come at you. Now, B now says, right? B is asking for what is the average downtime for a machine that is broken, i.e. the time from the breakdown to the time the machine is fixed. Come over here, right? And you're looking for a time, right? So the time you're looking for is W, right? I'm going to explain that. You're looking for W. See how I did it? A question sign W. The reason I know it's W is because it says, i.e. the time from the time it's broke down, machine broke down to the time it's fixed. So it must have been gone through the line, right? And then gotten fixed or serviced. Remember that thing I showed you? So that's system, right? That has to be system and not queue. Didn't say how long it's been in a queue. It's how long it's been in the system, right? Because it's being serviced. But you got that?
Yes, sir.
From queue to service. So it's the entire system you're talking about, how long it spends in the entire system. So then, my W is equal to my WQ, formulas are right there, plus 1 over mu. So I have mu because it's 3, but I don't have WQ. So then I have to find my WQ. WQ is going to be equal to LQ over lambda. And this is another reason why I like to put at the beginning what I'm trying to look for, because if you're working all the way down, you might get to a point and think you found the answer to the question. But until you found W, you have to answer the question, right? Just like a lot of you in the exam, I ask you for the linear regression equation. So you find B and you find A and you leave it at that. You can't do that. You have to tell me what the equation is. Y is equal to whatever, A plus BX, whatever, and whatever A is and whatever B is. Anyway, we'll talk about that probably next week. All right, so WQ is LQ over lambda. I have my lambda from up here, but I don't have my LQ. So LQ now is equal to lambda squared over mu minus lambda. I can get to going with my numbers now, because these are all lambda and mu, so I can do some calculations. There's going to be 3 squared, because lambda is 3. There we have it, 3. Mu is going to be 8, bracket 8 minus 3, yeah? And that's going to be equal to 9 over 8 5 is 40. What do I get there? 9 over 40, guys.
0.225.
0.2, I'll just put
23.
okay, 0.23. Now I can work back up. So WQ then is going to be equal to 0.23 divided by lambda, which is 3. And what's that equal to?
0.075. 0.08.
8. All right, yeah, sounds good. So now I found W, but remember what I'm trying to get is W. I mean, I found WQ. What I'm trying to get is at W. So now W is going to be equal to WQ, which is 0.08 plus 1 over mu, which is 8. So what's my W? What's my time spent in the system? Or the unit spent in the system? What's that? Just stuff 1 8 and you add 0.08 to that. 1 divided by 8 plus 0.08. What's that? Come again?
0.925.
0.93.
3. Yes, sir.
0.93. And now that I have my answer, I need to put my units. And it's days. Is that correct? Everybody got this? That look a little off to me. That don't look right. Somebody else?
Sir, I got 0.205.
Thank you.
Yes, sir.
Yeah.
Why would you say something? Why? 0.2.
205.
0.2. 0.21 then, right? Days. But remember now, the time we're talking about, and our rate was in days. So you have to come back to it's going to be days. All right. All right. So that's your answer for B. Now C's asking for. She says, how many machines are waiting to be serviced at any time? So it must be a L, right? How many machines are waiting? So they don't reach the service part yet. They're waiting. So it must be LQ is what they're trying to find. Looking for you. You have found LQ already from up here. LQ equals 0.23. And that's going to be units. Make sure you have the units every time because you're going to lose marks if you don't tell me what the units are. Okay? Dino is asking, everybody see I get LQ? Look at the question. That's how you know what you're trying to find.
Yes, sir.
Many. So it must be something with an L, right? How many machines are waiting to be serviced? So they don't reach the service yet, so they're still in the queue. So it must be LQ. All right, Dino says, what is the probability that more than one machine is broken and waiting to be repaired or being serviced? Now, you guys would have done probability in another course, right? A prerequisite course, am I correct? Yes or no? Yes or no? You did probabilities in
Yes,
another
sir.
course? All
Yes,
right.
sir.
Yes, sir.
Okay. So then, what's the probability that more than one machine
Is broken and
broken
waiting to be repaired.
So you're talking about the entire system. So you need to find this. P greater than 1. That's what you're trying to find. Probability of P greater than 1. So to do that, if you recall, it's going to be P is greater than 1. It's going to be equal to 1 minus bracket P naught, no machine in the system or waiting, plus P1, one machine in the system. You guys remember that? If you don't, that's how it's done. Anything greater than is just 1, subtract, and you get all the other stuff. So it's 1 minus P naught plus P1. That's a big deal. More than one machine waiting to be repaired. All right. So yeah, that's 1. Let's move on to question 2. I'll do question 2 also. Then I'll let you unleash you on all the other stuff, some fun with it. I know this looks easy, but this is where a lot of students lose marks. And a lot of times because they can't find lambda over mu correctly. You might think it's simple, but it's not. Well, it is simple, but people always get tripped up. All right, so let's go to question 2. Okay, question 2 says, Friday's car wash at the UTEC barn estimates that dirty cars arrive at a rate of 10 per hour all day Friday, right? With the Hottest Girl crew working the single wash line, right? It is estimated that cars can be cleaned at the rate of 1 every 5 minutes. 1 car at a time is cleaned. Again, just 1 car is serviced, right? That's our model. Assuming person arrival and exponential service times, find A, average that, B, that. But first things first, find your lambda and find your mu. Yes? All right, so let's see where we take that to. What's our approach for that? Okay, so. So, what's our lambda and what's our mu? So, this is probably going to surprise you a little bit. But your lambda, it says the arrival rate, the cars arrive at a rate of 10 per hour. 10 per hour or 10 cars per hour, with those cars we're talking about, 10 per hour, right? And they can be serviced 1 every 5 minutes. So what would this be? Your lambda is going to be 12 per hour. Have to be the same unit. I did say that, right? How you get the 12? It's 1 every 5 minutes. So you need to look at 60 minutes make an hour. So how much can they do in 60 minutes or an hour? It's going to be 60 divided by 5. And that gives you 12. That's why you get to 12 per hour. Is that clear, everybody? It's still 60 minutes in an hour, right? Or has that changed? I'm just trying to make sure we're on the right track. It's still 60 minutes make an hour.
Yes, sir.
Yes, sir.
Okay, so that has to change. So that's how you get to 12. So let's try to see where we're at. So your lambda over mu is equal to 10 divided by 12. What do we get here? That number, 10 divided by 12, 50 guys.
0.833.
3. That?
Yes, sir.
All right, so we're looking good, right? 0.83. So then, let's look at A. What is A asking for? It says average time, average number of cars in the line. So right away, I'm looking for L, and it's in the line, so it's LQ. So find LQ. My first can sign, that's what I want. And now I move over to the equations. LQ is equal to lambda squared over mu minus lambda. And that's going to give me 10 squared over 12 minus 10. That's 100 over 24. What's my LQ? What's the outside? 100 over 24.
4.17.
4.167.
0.17. And what am I talking
Yes.
about? Number of cars. From the problem is cars, right? So that's my A. My B, it says average time a car waits before being washed. So what am I looking for? A time, and it's waiting before it's being washed. So it's waiting before it's being serviced. So what am I looking for? Anybody?
WQ.
The wait.
Q. WQ is what I'm trying to find. WQ is equal to LQ over lambda. Lucky for me, I have LQ already. So it's 4.17 divided by lambda, which is 10. So my WQ is equal to what?
0.4.
0.4. I'm going to take this. 417. It's okay. I'll take it just because it's like that. And that is what? Hours. See it? Hours. If it says 0.2, that's fine. Hours. All right. So I've gotten that. What's a C is asking me from? C is asking average time a car spends in the system. So what am I looking for here?
W.
Double.
And W is equal to WQ plus 1 over mu. So you need to write formulas because you get marks for us identifying which formula you need to use, okay? So W is equal to WQ, which is 0.417 plus 1 over mu, which is 12. And what do I get here?
0.50.
What's the unit?
Hours.
Hour. So that's half an hour basically. You see it? 0.5? Yeah? It's about half an hour basically. And what is D asking for? Utilization rate. And you have that already, right? Yeah. PW is what you're looking for. But you have it already. It's lambda over mu. Utilization rate is 0.83 or 83%. So the car wash is busy 83% of the time, right? And then what's the next one? What's the probability that no cars are in the system? What are we looking for here?
P naught.
P naught. P naught is equal to 1 minus lambda over mu. You have lambda over mu already, which is equal to 1 minus 0.83. So your answer is equal to
0.17.
0.7. And that's a probability, right? So you don't have to do this for that. If you want to put it to a percentage, you can say 17%. Easy enough, right? Only issue you guys should have is up here, and it's not really an issue, to tell the truth. This queuing system is really, really easy. All right, but we're going to look at some more difficult ways of how we can determine certain things. All right, guys got that? All right, try your
Yes,
hand.
sir.
Try your hand at question 3. Question 3. I give you a couple minutes quickly just to give me your lambda over mu. And let's see what it is that we're trying to look for, okay? So direct message me your lambda over mu. Celine, that's correct. So keep going. Michael, that's good too. Teresa, that's good. Nobody else has got their lambda and their mu. Guys, there's 14 of you in the class. I've only seen 5. Now you see why I don't like to record tutorials, because you guys are supposed to be working the problems and you're not. And all you want to need to do is to record so you can go over it and you do whatever it is that you're doing in the class, because we're online. So I'm not even sure this will be posted, to be honest with you. This is a tutorial session, not a lecture. Tutorial session is where you work the problems. When you have issues, then you ask me to help you in solving those problems. Danique, that's correct. So Janet, remember, that's not correct. Remember, we said lambda must be less than 1. Lambda over mu must be less than 1. Odin, no. Remember, we said lambda over mu. I gave you a range to look at, which is kind of, between 0 and 1. I'd say anywhere from 0.2 to 0.9, because remember, it's also your utilization rate, your lambda over mu. So it's usually going to be anywhere from, say, 0.1, which is very inefficient, to 0.9, which is very efficient. So you're using up a lot of the capacity that you have if you get to 0.9, right? So it's between, Janet, yeah, that's correct. That looks right. Odisha, that's correct. Marie, that's correct. Janelle, that's correct. O'Kinney, no. Anybody finish? Anybody finish this entire problem yet?
Yes, sir.
You're done? So what did you get for your lambda over mu since you're finished? Huh?
0.8.
Okay, that's correct. All right. So all right, let us look at it for those who are still struggling with something this easy. Let's look at it. All right.
So the answer that I sent you was for the probability that it's empty, you know.
Oh, yeah, that's correct.
Yeah. Okay.
You don't just send the question, just answer like that. I wouldn't know what question you're referring to.
That was the first question. Somebody just got to that and work it. All right.
We had said what is lambda over mu, remember? All right, so Lucia Fruit has just opened a new cafeteria in Papine Square just for university students. This is a self-serve facility in which students select the food items they want and then form a line to pay the cashier. Students arrive at a rate of about 4 per minute, according to a pass-on distribution, right? The single cashier bringing up sales takes about 12 seconds per customer, right? And that follows an exponential distribution. It says That's the probability, how long, that. So quickly. First things first, what's our lambda? What's our mu? Our lambda, some people got is gonna be 4 students per minute. 4 students per minute, right? And so our mu has to be, we need to convert that because it says the cashiering takes about 12 seconds per customer. Maybe I should, customer student doesn't matter, all right, team student, because the students are the customers. So put the customer or student there. There's gonna be 5 students per minute, or just 5 per minute. Well, you get that? 12 seconds, so there's 60 seconds in a minute. Now we're talking about minutes, so you can divide that by 12 and you get 5. So 5 and 4. So our lambda over mu is equal to 4 over 5, which is equal to 0.8. So we're in business. It conforms to our model. A says, what is the probability the system is empty? Probability the system is empty is probability that there are no units in the system, right? So we're trying to find P naught. P naught is equal to 1 minus lambda over mu, which is equal to 1 minus 0.8 equals 0.2. All right, or 20%. B. How long will the average student have to wait, right, before reaching the cashier? So what are we trying to find here? Everybody?
WQ.
WQ, because before they reach the cashier.
So I'm gonna get 0.8 for that.
WQ is going to be equal to lambda
And the square.
LQ over lambda. Right, so to find LQ. So LQ is equal to lambda squared over mu minus lambda, right?
Yes, sir.
So that's going to be
16 divided by
it's gonna be 4 squared over 5,
and bracket minus 4.
so 16 over 5.
5.
What's that?
There's 3.2 students.
Well, that's not what you're trying to find. So you can keep going until you come to the end.
So lambda is supposed to be 3.2 divided by 3.
Is equal to 3.2 over
Divided by 3.
divided by lambda, which is 4.
4.
Yeah, 4, yeah, sorry.
So WQ is equal to what's that? 0.8
0.8
0.8.
minutes.
minutes. So let me ask you guys this. Would it be correct to say 0.8 minutes? What does that ask? It's almost like a joke. Because remember, it's not, anyway, it's not to get into it. It's not more than 1 minute, right? You know what I mean? You guys see what I'm trying to say, right? Believe it or not. All right, so where are we at now? C. What's the expected number of students in the queue? That obviously is LQ.
LQ. 3.
LQ already, right? 3.2 students. And D is asking what's the average number in the system, entire system now, so it's L. That is what we're trying to find. L is equal to LQ plus 1 over
Plus,
Q.
no.
That's equal to 3.2 plus 1 over 12, 1 over 5. What's that? 1 over 5 is what?
0.2.
What's the total answer then?
3.4.
3.4.
That's it. Easy, eh? All right. I want you guys to take on question 5. Take on question 5 now. Can take a snapshot of this quickly. Take on question 5. Can I move to the problem now? Can I put on the problem now? You guys have everything on the board here?
Sir, for D, is that L equal LQ plus 1 over mu?
Yeah, the equations are over there. So if I'm down here, it's kind of because I'm kind of tall. Just
When I'm looking at it on the other side, it's saying LQ plus
lambda
mu,
over mu.
lambda over mu.
You're correct. Thank you. So this is incorrect. Right, you're right. You are right. Yeah. Lambda over mu. And you know lambda over mu is 0.8, so it's going to be equal to 4 students.
4, yes, sir.
Yeah, I knew something kind of seem a little off. All right, so that's it. Let's go to question 5. Thanks for that.
So we're skipping 4.
Yep. A lot of problems. I'm not doing all the problems. You're gonna have to do some of them on your own. Question 5, though. I want to do question 5. So try question 5. Couple minutes, and we'll do it. Question 5.
So what's the probability that one customer is receiving? Probability. That you system. From A and B. What's the probability? What is the probability that one customer is receiving return? How long will it take? What's the probability? The next probability. Times to 8. Probability. Any excuses contribute to being using the system. Sir. Sir.
Okay, anybody finished?
Sir, we're stuck, sir.
Stuck. All right. So let's go.
Yes, sir.
So had I put this one in the exam, everybody would have what have I gotten it wrong?
Well, I attempted, sir, so.
Would have made an attempt, sir.
All right. All right, Blackbeard Barber Shop has one barber. Right? Customer arrive at a rate of 2.2 customers per hour. Haircuts are given at an average rate of 1 per 20 minutes. Use pass on arrival as an exponential service model to answer the following question. Was it probably no use in system? It's probably one, all that kind of stuff. All right, so. First things first, what's your lambda, what's your mu? Everybody?
2.2 and 3.
2.2 hours for lambda.
Hours.
Per 2.2 per hour.
Oh,
And
And then mu is 3 per hour.
everybody, shall we get that?
0.73.
What did you get? How much?
0.73.
0.73.
We're going to get the 3 hours there. Where are we at? Yeah. 60 over 50. That's what you get. All right. That's what you get the 3. Everything was. All right. So A. So we're good. Lambda over mu is 0.73. So it fits our model. It says, what's the probability that there are no units in the system? So we're trying to find P naught, right?
Yes, sir.
And P naught is going to be equal to 1 minus lambda over mu.
So 1 minus 2.2.
Minus 0.73. The answer for that one will be 0.27
0.27.
or 20%. Now B asks, what is the probability that one customer is receiving a haircut and no customer is waiting? So what we're trying to find? Anybody?
I said I was trying to find PM,
Where N is what?
where N is 0.
No.
1.
1, sorry.
1, right. N has to be 1. So trying to find P of 1. And that is equal to
0.7.
over mu. With 1 4 times P naught. So that's 0.73 with 1 to the power 1 times P naught, which we got, which was 0.27. So what's that answer?
I got 0.2.
0.2?
Yes.
I don't know, I'm just asking. All right. So now what's B? What's C? C says, what's the probability that one customer is receiving a haircut and one customer is waiting? What are we trying to find? Buddy? Huh? Trying to find P of 2, right? In the system. See, there are 1 receiving the haircut and 1 is being serviced. So many people in the system.
That's how we do it, sir? Oh, Jesus.
Repeat that, way, sir. I didn't hear what you said, sir.
Says 1 customer is receiving a haircut. What are we doing? C, right?
Yeah.
Okay.
And 1 is waiting.
Yes,
So 1 waiting here. And so the one over here receiving the haircut. So 2 people are in the system. Remember? Probability N units in the system. See it? So P is 2. So P2 is what you're trying to find.
So would that be 2 plus lambda over mu
So all is going to
2?
be lambda over mu, which is 0.73 squared times P naught, which is
0.27, which equal to 0.15. That's what I had.
equal to
0.15, but 0.45 something. 0.145 something.
15 calculators. What is the answer for this?
0.15, sir.
Okay.
Because I did it.
That's why you did it. Somebody check that to make sure it's correct. 'Cause, I mean, and then D,
Oh,
now.
and 145, so.
Huh? Okay, D says, what's the problem with one customer receiving a haircut and two customers are waiting? What are we trying to find?
Q,
Probability of
E3.
3.
P3.
Yeah.
That's what we're trying to find. So P3 is going to be equal to lambda over mu, which is
0.73
Q
cube times 0.27.
0.27. What's that?
Zero point 11.
Sure? Did somebody confirm that? E. What's the probability that no more than one customer?
Let's see, how should it be 0.15? Shouldn't it be 0.14?
That
Where?
is 0.145. That is
That's
0.1.
what I got. It's 0.43. So you just leave it at
How many times I ask you guys just to check the numbers? I have to do it. What's his answer for P2, guys?
0.143.
4.
Oh, 4. Okay.
144.
All right.
0.14.
That's fine. It doesn't matter. All right. Next. Yeah. So this is correct.
Yes, sir. 0.11 is correct.
He says,
Yes, that's correct.
all right. He says, what's the probability that more than one customer are waiting? We're trying to find it. All you have to do is go back to what I've showed you. Waiting. So 2 customers is waiting. That means a 1 must be there. So what you're trying to find is that P is greater than 3 because it's in the system you're talking about. 2 waiting. Anytime 2 is waiting, that means 1 must be getting service, or 2 wouldn't be waiting. It would only, if 1 go over, then there's only 1 waiting. Are you seeing that? 2 in the queue, are you seeing that? That means 1
Yes,
must
sir.
service. So you're trying to find greater than P3. So greater than P3 is equal to this, 1 minus bracket P0 plus P1 plus P2 plus P3. All of which you found already. See it? Yes, no, maybe so.
Yes, sir.
Okay. And F basically is asking what's the average time a customer waits for service. What we're talking about? WQ, right?
Yes, sir.
And you guys can find that, please. All right, so that's it. Nobody would have got this right. Well, who is it? Chance?
Will I get up to D?
Right. So
I'll get A and B and S.
F. I'm gonna get U.
right. So now you can get everything on that, right? All right. Here's what I want you guys to do. Start it. No, I don't want you to run ahead of the other class. So we have to end here, yes, the other class, because persons have to go register for some stuff. So I want you guys to try question 6. 6, 7, 8, and 9. Why not? Just try them. Right? Let's start now with question. Yes, 7 is kind. Okay, quickly. We're gonna try 6, 7, 8, and 9. All the problems left. But quickly, let us quickly. You guys try question 8. Just tell me your lambda and your mu for question 8. Hear that? Question 8. Just give me a lambda, give me a mu, because obviously you'll be able to do everything else after that. Give me a lambda, give me a mu for question 8.
4.5 minutes and 2.8.
No, you direct, yeah, direct.
Okay,
Message.
so 4.5.
Give everybody else a chance. Just direct message me, please. Give me a lambda and your mu. And then your lambda.
Question 8, sir.
Question 8. Is 8 or is it? Let me see this. Question 8. Wait, let me see. No, 7. 7. All right, 7 and 8. Give me the lambda and the mu. Let's go faster. 7 and 8. Give me the lambda and the mu for 7 and 8. The lambda and the mu for 7 and 8. That way we'll save ourselves some time next week. We just have to work. Lambda and mu for 7 and 8. Lambda over mu also. Let's do this quickly. Everybody get 24 over 30. Lambda over mu, 24 over 30. You might have worked it another way, but you should get what 24 over 30 comes to. Everybody seeing it? Yes
That's
or
the
no?
number 7, sir.
Huh?
Number 7. you're
No,
talking
sir.
about?
Yeah.
Number
I got the
7.
same. I got the same.
Lambda over mu,
Yeah.
0.8.
0.8. Yeah.
As long as you get that, you're good. The lambda over mu must be less than 1. So what I did, I converted everything to hours, right? So 4 every 10 minutes, that means in 1 hour, it's just 60 over 10 times 4, right? So to convert it to hours. And then it's going to be the service time is 30 minutes because it's 1 or 30 per hour because the service time is 2 minutes, right? So in 1 hour, it's going to be doing 30. So you get 24 over 30 next. And the other stuff you can do with.
So if you do it this way,
You'll be
sir,
fine. As long as your lambda over mu is correct, you should be good. Yeah, I got 0.8. And you did it the other way where you did it in minutes. So it's 10 every 10 minutes.
4 every 10 minutes, sir.
4 every 10 minutes. So what would that mean every minute?
5 every. So the average, sir, 7 every 5. So the mu would be 5.
Your what? Your what?
The mu would be 5.
You, what is lambda? What is lambda?
And that is 4. 4 every 10
So
minutes.
you're working every 10 minutes. No, they have to be careful. So what you're doing is 4 every 10 minutes, you know. So be careful of that. That's not every minute or per minute. That's per 10 minutes. So be careful when you want to turn around, you might get yourself into trouble. Try to bring it to 1 unit. 10 minutes is not a real unit. That's per 10 minutes. You understand what I'm trying to say? So bring it to a 1 unit. So per second, per minute, per hour. The easiest way I see is to take everything to hour. It's a larger up your.
Let's say 4 every 10 minutes is
150.
It's 24 per hour.
24 per hour, sir.
Yeah,
Right.
times 4 by 6.
Right, and then
Extend
average time, average service time is 1 every 2 minutes, so every hour is gonna be 30. 1 every 2 minutes, therefore, how many can you do in 60 minutes?
It just divide basically.
So that would be 30, so it's gonna be 24/30 is your lambda over mu, all right? All right, the burger, let's see this burger one now, because question 8, got question 8. Matt Burger fast food as a drive-through window with a single server. Window operated by other employees to prepare orders. Customer arrives at the order station prior to drive-through window every 4.5 minutes. And the service time is 2.8 minutes. So let's see if this is correct. One of those problems was given to me. This one was that one.
13.3.
It can't, it must,
Mm.
lambda over u must be less than 1, eh?
Oh, yes, sir.
So one of these problems are giving us some issues. I think it might have been this one. Yeah. These numbers are incorrect. Okay. All right. So
Sir?
yes, go ahead.
Oh, I was asking to repeat what you just said about incorrect.
No, I think question 8 is incorrect. The numbers.
Sir. It's
But
incorrect.
let's look at it. Lambda
Lambda, it calculates
4.5.
lambda is 1 point something.
every minute is 4.5, and service time. So maybe not. Let's see. Every 4.5 minutes. So for every hour.
So I got 13.3 divided by 21.4.
Oh, so it's good.
0.62.
Per hour. You do per hour.
Yes, sir.
Divide by 4.5. So we arrive at the rate of 13.3, right? And 13.3,
And mu is 21.4.
right? So that's fine.
Right, it's 0.62.
Yeah, so it's okay then. Yeah.
Okay.
All right. I was checking. Yeah, so it's fine.
0.62, sir.
All right.
Alright.
Good. All right, so that's fine. All right, guys. So I want you guys to try question 6. Question 9. 6 and 9. All right. The others, what we just did a while ago, is easy. So 6 and 9. So you can start working question 6. Sometimes your mu will change. Sometimes your lambda will change. So you to know how the change come about and what it will cause. So 6 and 9. All right, and that's it for the class today. Question 6 and question 9. That's all you guys have to do. Question 6 and question 9. All right, guys. So this is where we're gonna end it today, and I will see you guys next week. So enjoy the rest of your weekend.
Yeah.
All right.
So I send you an email so you can
6
check
and
it.
9. We worked enough of those problems. Work them between yourselves in groups and come up with your answers. We worked enough of these problems.
Yes, sir. Question.
Work a whole lot of those
Yes.
problems. I'm not going to work anymore at linear programming. I've worked about 7 problems in all on the sheet.
Yes, sir.
Work them amongst yourselves and come up with answers. Just as if you were doing a test or an exam and you work together and you come up with answers. I've worked enough of the examples. I've worked at least 6 or 7 examples for you. Yeah, somebody was saying something.
Yes, sir. I was going to ask if there is any feedback as it relates to test 2.
Test 2, you only did that last week.
Yeah, what the last time
Yeah.
you
No,
provided response within a week.
I have a lot more stuff this time, so I have a lot more stuff to do. So I'll get you that. Who was asking? Who's that?
It's far low.
All right. Okay, yeah, I'll get you those. Maybe I'll send them out next week sometime. You'll have them. All right.
Sir, I sent you an email. Yeah. It's from my work email because I'm on an operation. So just to the UTech email.
No, I said it's fine. You said it came up late or something like that. I sent you
Yeah,
back.
I
Say
said
it's
it will
fine.
get on. Okay, cool.
Yeah.
All right, no problem. All right.
Okay. Anything else? No? All right. So those guys, the linear programming problems, guys, you need to work them out and work them as a group, find the answers. You guys must can work in a group and solve those. I've done enough of those examples. All right. All right, so that's it.